In this video, we're going to be discussing the numerical and analytical representations of the derivatives. So let's take a look at our first example here. Here are the numbers from the last four different censi to record the population of British Columbia. The questions ask to first of all find the average rate of change of population between the 2 years, and then to approximate a derivative at one particular year, which is 2011. So for the average rate of change, we always take the beginning and the end points and calculate the difference between the two. And what that translates to, if we plug in the numbers for the actual population sizes, so I had 4,648,055 minus the population 2001, which is 3,907,738, all over the 15 years that went in between, and the number comes out to be approximately 49,354. Now, of course, there's decimal places, but I'm just going to round it to the nearest person. So this is then people per year. Okay, and so again, that means that on average, the population of British Columbia was growing by 49,354 people per year over that span of 15 years. If we were to quickly sketch that on a graph, the average means I'm taking it between 2001 and 3.9 million people, and 2016 and 4.6 people. So the average is the slope of this line connecting the two. Now, of course, that means that anything could have happened in between. Maybe there was first a huge increase and then a decrease, or maybe it was, increasing and then decreasing a little less drastically. Anything could have happened in between. The average will only tell us so much, which is why it is much better to approximate things like this by estimating the value of a derivative. Here we're asked to approximate the derivative in 2011 of the population in 2011, which means we would like to approximate instantaneous rate of change in year 2011. Now, the problem, of course, is I have to pick some points to calculate in between. And in 2011, if I'm approximating the derivative, I don't have the actual function in where to plug it in. I am forced to use the points that I have. So if my year of interest is 2011, in order to get as good of an average, as close to instantaneous rate as possible, I'm going to take the points that are as close as available to 2011. So here, it's still not going to be great because I am then forced to use years 2006 and 2016 that are each 5 years apart from 2011, but those are the closest points that I actually have some information on, right? So the average is going to be approximately the population size in 2016 minus the population size in 2006 divided by the difference between those two numbers. Now, if I calculate that correctly, this comes out to be 53,456. And once again, I am just going to go ahead and round into the nearest person. So I'm not going to have any decimals here. So this is people per year. If we sketch this on the graph, that means that I'm now computing the slope of the line between the data point in 2006 and the data point between 2016. So here I have something like this. And I can indeed see that my calculations actually support what I'm seeing on the graph in the sense that the line between the 2006 and 2016 data is steeper than the line from 2001 to 2016. Now, again, this is not great because my closest available points were 5 full years apart, but this is all the data that I have. If I have an actual function, I can do much better in terms of how closely I want my points to lie. So going back to our application on estimating the age of a fetus and the femur length formula, this is the actual function behind the graph that we saw last time. Here, I am asked to once again approximate, but now the instantaneous rate of femur growth in 20 weeks using the formula as opposed to using the graph that we did last time. Okay, so here I'm still just approximating. We don't yet know how to compute we're going to talk about it in a little bit, about how to compute derivatives exactly. So the best I can do is approximate it. So 20 weeks, that means I have to pick 2 points near 20 weeks. And here, this is where approximation is going to come forward, is, well, how close do you want to be? So for example, how about 19 weeks and 21 weeks? If I compute the average between those 2 weeks, that's pretty close to 20. 20 is just 1 week in between, right? So that average is going to be pretty close to instantaneous. But what about if I wanted to get closer still? So like 19.9 weeks and 20.1 weeks, or 19.99 weeks and so on. The formula gives me the freedom to get as close as I want, as opposed to the table in the previous example, where I was restricted to the numbers that have already been provided. Here, I can decide my own threshold for it, okay? So we're actually going to compute those two. So the average between 19 and 21. So I'm going to plug in 21 into my formula and 19 and divide by the 2 weeks in between, and the number comes out to be 2.9498. The units are whatever the units of my top measurement were, which were millimeters, over the units on the bottom, which were weeks. So this is millimeters per week. If I compute the average over, I guess the average is actually, it does equal to that. If I compute the average over the slightly smaller period of time, so between 20.1 and 19.9, and I'm going to divide by the difference between two. I'm actually going to write this out, so that's going to be 0.2. This is now approximately 2.9505 millimeters per week. So I'm seeing now that if I take 2 week period, it's approximately 2.95. If I take a 0.2 week period, which is very short, like really, it's just about a day, then it's about 2.95. So I can be fairly certain in saying that instantaneous rate of change in 20 weeks, instantaneous rate of FEMA growth at 20 weeks is approximately 2.95 millimeters per week. Is approximately. Now the thing is, of course, none of that is exact, so I have to include the words approximately millimeters per week. One other thing to notice here is that this function is a polynomial. The numbers are ugly, like the coefficients are not the prettiest, but you can notice that the only time the variable appears is in t and t cubed, which means it's just a cubic function. So polynomial functions don't have any unexpected holes or cusps or corners, which means that I expect the derivative to exist. So I know that nothing really drastic can happen at t equals 20, and then my approximation is going to be fairly close. Remembering what we did last time when we computed the exact same thing from the graph, let's just remind ourselves what graphical representation means. At 20 weeks, that meant computing the slope of the tangent line at 20. And when we had the graph, the best we could do is eyeball some points from the graph. I believe my approximation then was approximately 2.5 millimeters per week. We now numerically have a obviously much better way to calculate it, and I was able to take points that were much closer as opposed to the graphical calculation, when I believe I chose points to be at like 14 and 20, so 6 weeks apart. The closer the window, the better your actual approximation. So from the graph, the window was much wider at 6 weeks, whereas in calculations, I can make it as small as possible. Okay, so you can go even closer than that still. For approximation purposes, it doesn't really matter. Now, no matter how close I go, I can always go closer still. So how close is really the best, the closest possible? And the answer is, of course, the best we can do is to actually use the limit definition of the derivative and calculate as limit goes to 0. So as the difference between those 2 points that you're computing in between is actually non-existent. So we're going to take a function for our first example that's not an application, because I don't want big ugly expressions, we're just going to take a function 5x. And I would like to go through the actual definition of the derivative to see how I can compute the derivative exactly. This is the one time using the analytical representation of the derivative. This is our first time computing the exact value of the derivative. Not approximation, but an exact value. Okay, so in the definition of the derivative, I have the function, first of all, f of x, but then I also have f of x plus h. So we're going to have to compute f of x plus h. Now, so function notation is really crucial for computations with derivatives. If you're still not comfortable with this, please go back to the pre-calculus review package so you can practice it some more. But what that really means is that everywhere I see, whatever I see inside the function, I have to put in the output, right? So here, this was x and x. If I'm computing the function at x plus h, it means that my x plus h has to replace every single occurrence of x in my function throughout. So here I'm going to then have x plus h on times 5, okay? So notice that, and this is the biggest mistakes that students make, so please take a note of it now so you don't fall into this trap. This f of x plus h is not 5x plus h. This h is not an afterthought. This entire x plus h has to replace the x in my function here, okay? So think of that as one unit. It used to be x, it's now x plus h. It has to all come together, okay? So now that we've computed this, we can simply plug in everything that we have into our definition of the derivative. And now I know that instead of this, I should have 5x plus h, and instead of my function, I should have 5x. So putting this all together, I have the limit as h goes to 0 of 5x plus h minus 5x all over h. Now, first rule of limits, I'm going to try to plug it in. Here, h is 0, so the first step in plugging in, I noticed that it's still in the bottom, so I can't just plug it in. I'm going to do some simplifying, and I can see that the easiest thing I can do is just open up the brackets on the top. Okay, so I'm going to have 5x plus 5h minus 5x all over h. Now, of course, it's easy to notice that 5x and 5x cancel out. So I have limit, I haven't computed the limit itself yet, of 5h over h. Well, this is great news because h's just cancel out. So I have the limit of of 5 as h goes to 0. I can plug it in. There's actually no h's anymore. So the limit of a constant is just a constant itself, so it's 5. So that means that for my function, if f of x is actually 5x, then its derivative at any point x is just 5. So this is the one case when the derivative is actually constant. And let's just make sure that this corresponds to our graphical understanding of what a derivative is. The function is 5x. So if I were to sketch that, 5x is just a line, right? This is a line with slope 5, so it's like mx plus b, but there's no b, b is 0, so it's actually going through the origin. So it's a line of slope 5 through the origin. If I am to draw a tangent to this function at any point, it's just going to be this line itself, right? So its tangent is itself, and the derivative is the slope of the tangent line. Well, what is the slope of this function? The slope is 5. A line has a constant slope of 5, so slope is 5 everywhere. So for the line, it really doesn't matter when you take a derivative, it's going to be 5 everywhere. That's the one time when the derivative is actually constant. In all other cases, the derivative will also depend on x itself. And you're going to see more examples going forward about how to do this. Please practice substituting different functions into this difference quotient is what it's called, to make sure you really are comfortable with the function notation, with the simplification, and with the computing of the limit as the last step.